Hey everyone, this video is all about determining limits using algebraic manipulation and the algebraic properties of limits. So far we've used a graph to estimate limits, then we used tables to evaluate limits. Now we're going to start looking at what algebraic things can we do to evaluate limits. So this wasn't from an investigation. We ended up not doing that this year. However, what we want to talk about is if you evaluate f of a, and f of a is a real number, so it's not undefined. It's not a piecewise where a is the breaking point. So as long as those two things don't occur, if you get f of a and it's a real number, then the limit as x approaches a of f of x is simply just f of a. In other words, all you have to do to find a limit, provided that the function value exists at that spot, all you have to do is plug it in or substitute it, if we want to get a little bit more mathematical there. All right, so let's look at a couple examples. So the limit as x approaches 5 of x squared minus 4x plus 3. All we're going to do is take this x value and we're going to substitute it for x. So 5 squared minus 4 times 5 plus 3. So let's see, 25 minus 20 is 5, plus 3 gives us 8. So the limit as x approaches 5 of this x squared minus 4x plus 3 is equal to 8. We're going to do the same thing here. All we have to do is plug 1 in anywhere we see x. So 1 to the 7th minus 2 times 1 to the 5th plus 1. And that whole thing is inside of parentheses. We're raising it to the 35th power. Excuse me. So let's see, 1 minus 2 is negative 1, plus 1 is 0. So we get 0 to the 35th, which is just 0. And then here we're going to take that 2 and plug it in for x. So 5 times 2 to the 3rd plus 4 all over 2 minus 3. So let's see, 8 times 5 is 40 plus 4 all over negative 1. So negative 44. So a lot of times being able to evaluate a limit really just means substitute that value in and get an answer. Now there are a few cases where that's not going to work. So for example, with piecewise functions we have a little bit of a difference here. So for one-sided limits, all you're going to do is try substituting the x value into the appropriate side of the breaking point. For two-sided limits, you're going to have to check both sides. And so what that means on here, though, is checking both sides is only important when the x value is the breaking point. So if the x value isn't the breaking point, all we have to do is substitute the value in, and it's exactly like numbers 1 through 3. If, however, the x value that we're trying to evaluate the limit at is the breaking point, that's when we have to check both sides. So let's first look at, here's our piecewise function. So we've got a parabola when x is less than negative 2, and we have this line when x is greater than or equal to negative 2. So when we look at this one, we can clearly see that the breaking point is at x equals negative 2. That's where we have an issue. So our breaking point is at x equals negative 2. That's when we have a problem, potentially, with our graph. So let's go ahead and start with the limit as x approaches negative 2 from the left of f of x. So if I'm approaching negative 2 from the left, then that means I want to be less than negative 2. So I'm going to be looking at the first part of this function. So negative 2 squared minus 8 times negative 2 minus 15. So let's see, negative 4 plus 16 minus 15. So I get that my limit is -3. So again, left-sided limit, I want to plug it into the function that deals with x is less than -2. And so I got -3 as my left-sided limit. Then for the right-sided limit, as x approaches -2 from the right side, that means I need to be greater than or equal to -2. So I'm looking at this portion of my function, which means I'm going to substitute -2 into this function. So I get 4 minus 6, which equals -2. Now I want to look at the limit as x approaches -2 of f of x. So we know that in order to look at a two-sided limit, we have to look at the left side and the right side, especially since -2 is our breaking point. Well, luckily we did both of those pieces right here. So if we look, we can see the left-sided limit and the right-sided limit do not match up, which means this overall limit does not exist. Because the limit as x approaches -2 from the left of f of x does not equal the limit as x approaches -2 from the right of f of x. Okay, now let's look at the limit as x approaches -3 of f of x. So what I want to point out here is that -3 is not our breaking point, which means I don't have to worry about checking both sides. I can treat this exactly like I treated numbers 1, 2, and 3. I just have to know which piece of my piecewise to plug it into. So since -3 is less than -2, I'm going to plug -3 into this quadratic function here. So -3 squared minus 8 times -3 minus 15. So I get -9 plus 24 minus 15, and so I get 0 for my limit. Again, I don't have to, oh, you can't see that, sorry. I don't have to worry about checking both sides because -3 is not the breaking point. So in this case, I can just substitute my limit value in and I'm good to go. All right, let's move on to the next part. So if you can, we just plug it in. If it's a piecewise, you got to think a little bit more, but still just going to plug it in. So the problems come up with what happens when you cannot just substitute, okay? So if we take -2, so the limit as x approaches -2 of x squared minus 4 over x plus 2, when we look at this, if I plug in -2, that's a problem because I would have a 0 on the bottom. So the first thing we can try is factoring. So when we look at this, I'm going to take this original function. I'm going to ignore my limit notation for just a second, and I'm just going to write x squared minus 4 over x plus 2. Hopefully when you look at the numerator there, you can see that that's the difference of squares. So I can factor that as x minus 2, x plus 2, and my denominator stays as x plus 2. Which means I can cancel these x plus 2's, and this function overall simplifies down to x minus 2. All right, so all I did was take out my function over here, factor, and I canceled things. So now what I'm going to do is I'm going to go back up to my limit. This is where the limit notation needs to come back then. So the limit as x approaches -2 of, now I'm just going to put in x minus 2. Because we decided that this function is the same as this one because I simplified it down by factoring. And so I can take this function out and just put in this x minus 2. Well, now I can actually just substitute. So if I take my -2 and plug it in, I'd have -2 minus 2. That means that this limit is -4. So one option is to try factoring and then go ahead and try to substitute. Take a look at number 2. If I plug 1 into this function, I'm going to have a 0 on the top and a 0 on the bottom, which is a problem. I'm going to zoom in a little bit if it'll let me. Ooh, that's too much. but that's better. Okay, sorry about that. So the second thing we can try is to multiply by a conjugate. If we look at this function right here, we can see that there's nothing for us to factor. So option 1 isn't going to help, okay? Option 2, though, is to try and multiply by a conjugate. So what we're going to do is we're going to take our function and I'm going to write it down below. So I'm going to move up a little bit so we can see. And I'm going to rewrite my function. It's x minus 1 over the square root of x minus 1. So a lot of times if you see a square root, that's how we know we're going to have to multiply by a conjugate. So I'm going to put both of these in parentheses because we need to make sure we're careful. And I'm going to multiply by the conjugate of the denominator. So I'm going to multiply by the square root of x plus 1 on the top and the bottom. Remember, if I multiply the same thing on the top and bottom, it's like multiplying by 1, so it doesn't really matter. Now, on the numerator, I'm not going to simplify anything. I'm going to leave it as x minus 1 times the square root of x plus 1. Because if I try to multiply that out, nothing nice is going to come from that. So I'm just going to leave it alone. Okay? Then let me move back here for a second. This is what I want to actually simplify. All right, so remember, because these are conjugates, we're able to multiply this out really nicely, but I'm going to go ahead and actually FOIL just in case you guys need to see it. So the square root of x times the square root of x is x. The square root of x times 1 is plus the square root of x. Negative 1 times the square root of x is minus the square root of x. And negative 1 times positive 1 is negative 1. So now I'm going to go ahead and move over here, and hopefully you guys can see these square roots cancel each other. And so now I'm left with x minus 1 times the square root of x plus 1 over x minus 1. If you could jump straight from the two conjugates to here, I'm totally fine with that. But just in case you needed to see it, I wanted to show you guys that. Now when we look here, these x minus 1s cancel each other. And so we are left with this entire thing simplifies down to the square root of x plus 1. All right, I'm going to zoom out a little bit. There we go. So now we can see this whole thing by multiplying by the conjugate, we simplified our entire function down to the square root of x plus 1, which means now we can go back up to our limit. So now I can find the limit as x approaches 1 of this new function that I was able to simplify down to, which is the square root of x plus 1. Now I can substitute. I get the square root of 1 plus 1, which simplifies down to 2. All right, one more thing that we can try if we're not able to substitute is to try eliminating the denominators. So if you see this crazy fraction in a fraction, we know that that's a place for us to try and eliminate the denominators. So, oops, there we go. I'm going to rewrite my complex fraction here. So it's 1 over x minus 1 minus 1 all over 1 over x minus 1. So I always start out by making sure that every single piece of my fraction is actually a fraction. So 1 over x minus 1, that's already a fraction. I'm going to make this 1 over 1. And then this piece here is 1 over x minus 1. So what you need to do is multiply by the least common denominator. So in this case, the least common denominator would be x minus 1. So I'm going to multiply that on the numerator of every single fraction here. And when I do that, this x minus 1 cancels with this one, and I'm simply left with a 1. And then here, nothing cancels, but I'm left with a minus x minus 1. And on my numerator, or I'm sorry, denominator then, this x minus 1 cancels with this one, and I'm left with a 1 overall on the bottom. So all I had to do was multiply by the LCD, and it makes this a lot easier to deal with. So now I can distribute my negative, and I'm at 1 minus x plus 1 all over 1. And this simplifies down then to 2 minus x. So this whole function simplifies down to a much nicer thing for us to be able to evaluate. So now I can go back up here. This is the limit as x approaches 1 of 2 minus x. And now I can go ahead and substitute. So 2 minus 1, my overall limit is 1. We're going to do tons of examples like this in class, so if you had questions, please make sure you wrote them down, and I'm more than happy to go through any of these again with you guys if you need me to. All right, now we need to talk about properties of limits. So, the limit as x approaches a of f of x is L1. The limit as x approaches a of g of x is L2. That's going to be really important as we work through these problems. So, the limit as x approaches a of f of x plus g of x. So if I take these two functions and I add them together, then I know I can take those limits and I can actually break them apart. So I can say that this is the same as the limit as x approaches a of f of x plus the limit as x approaches a of g of x. So if I'm adding the two functions and taking the limit, that's the same as taking the limit of each function and adding them together, which means this whole thing then can just become the limit as x approaches f of x, the limit as x approaches a of f of x, which we know is L1, plus the limit as x approaches a of g of x, which we know is L2. So really, you guys, it's a fancy way of saying if you're adding the functions and taking the limit, you can also just take the limit and add the limits together. Okay? The same thing is true for subtraction. So I can write this as the limit as x approaches a of f of x minus the limit as x approaches a of g of x, which means this simplifies down to L1 minus L2. Same thing for multiplication. So the limit as x approaches a of f of x times the limit as x approaches a of g of x, which means that's the same as L1 times L2. You're not going to have to worry so much about these notations necessarily, but when we get to these examples, this will kind of make a little bit more sense. So I know I'm kind of racing through this, but bear with me. All right, this next piece here is for division, so we can do limit as x approaches a of f of x divided by the limit as x approaches a of g of x, which really means L1 over L2. An important part here to be able to recognize is that that means L2 cannot equal 0, because if it does, we're dividing by 0, and that would be a problem. All right, this part here, we're taking the limit as x approaches a of the nth root of f of x. So really, we can take the nth root of the limit as x approaches a of f of x. So we can kind of take that radical and pop it out of the limit, okay? Which really means that this would end up being the nth root of L1. And finally, I know this is a lot, this here has a constant, this k. If you've got a constant inside of your limit, you can pop that out as well. So this can become k times the limit as x approaches a of f of x, which really means k times L1. Again, I know that's kind of weird, it's kind of a lot, but I'm going to do these examples here, it'll make a lot more sense. So, we were given the limit as x approaches 8 of f of x is -9. We were given the limit as x approaches 8 of g of x is 2. and the limit as x approaches 8 of h of x is 4. So we're going to use those three facts to be able to compute the following limits. So if you notice, we're not given anything else about these functions. This is where these properties come into play. All right. So the first thing that I am going to do is I notice that there's a subtraction here, which means I'm going to break up my two limits. So I'm going to go ahead and do the limit as x approaches 8 of 2 f of x minus the limit as x approaches 8 of 12 h of x. So the first thing I saw was that subtraction. The next thing I see is that there's a constant right here and a constant right here. And we just said that for this property, the constant can just pop out. So I'm going to go ahead and do that. So I'm going to take the 2 and make it 2 times the limit as x approaches 8 of f of x minus 12 times the limit as x approaches 8 of h of x. And now if I look, I can see those pieces that I wanted. So this is the limit as x approaches 8 of f of x. Well, I know that that's -9. Then this piece here is the limit as x approaches 8 of h of x. I know that that's going to be a 4. So now I can actually use those values that I was given. So it's 2 times that limit minus 12 times whatever that limit is. All right, so the orange one is -9. And the limit for h of x is 4. And then we can actually simplify. So we get -18 minus 48. So we get that our overall limit is -66. Okay, I know that's a lot. I know this video is getting long, so I'm going to cut it off, and we are going to talk about Part B in class when I see you guys on Monday. All right, again, sorry for the longer video. Have a great weekend.